When I was a kid, I was fascinated by the idea of solar sails. I read and watched a lot of science fiction that had solar sails, and honestly, the aesthetic is just unmatched. But are solar sails really possible? And if so, why don't we have them already? Well, that's what this video is going to be about. The first thing you have to know is that light has momentum. Even though it has no mass, it's going so quickly that it can actually push things. Look at this demonstration where a light being shined onto a small object in a vacuum is actually pushing it. He takes the light off, it swings back, he puts the light on, it gets pushed forward. Now that's pretty amazing. We have this not physical thing that is making a physical object move. The amount that the object is pushed depends on how reflective the object is, but assuming the object is perfectly reflective, the force arising from the radiation pressure is represented by the equation F equals 2IA over C. I is the intensity of the light, A is the area of the object, and C is the speed of light. In order to show how this would work with a solar sail, let's go ahead and put in some numbers. So first off, I is the intensity of the light. The intensity of the sun by Earth is just about 1300 watts per square meter. The area, let's say we have a 100 meter by 100 meter sail. So for the Americans, it's about the size of a football field on each side. That's 10 to the fourth meters. In that case, the force on that sail would be 0.086 newtons. Now, of course, we need something to put that force on. So let's go ahead and say that our solar ship has a mass of 1,000 kilograms. Using Newton's second law, force equals mass times acceleration, we see that the acceleration for this solar sail would be 8.6 times 10 to the minus 5 meters per second per second. That's not very much. That means in the first second, it's going to go about a tenth of a millimeter. But the great thing about acceleration is that it just keeps going. You get faster and faster and faster. It would take 3.2 hours for our ship to hit 1 meter per second. Let's compare our solar ship to the fastest man-made object, the Voyager 1. The Voyager 1 is an interstellar probe that was launched September 5th, 1977. It was one of a series of probes that was designed to use the gravity wells of large planets in order to accelerate and leave the solar system, which it did August 25th, 2012. Now, the Voyager 1 is going 17,000 meters per second. It is going incredibly quickly. Our solar ship is going to take a long time to catch up to it. But crucially, it will catch up. Even at that minuscule acceleration, because the sun is shining 24 hours a day, it would only take 6.27 years for our solar ship to reach 17,000 meters per second. And it would keep getting faster. Because acceleration is a little harder to grasp, let's go ahead and just talk about distance. First off, when talking about interstellar space, you generally talk in terms of astronomical units, or AU. Now, 1 AU is the distance from Earth to the sun, or 150 million kilometers. The solar system ends about 120 AU from the sun, and the Voyager is over 165 astronomical units away. That's 2.46 times 10 to the 13 meters from Earth. So how long would it take our solar ship to reach those distances? Here we have a handy-dandy acceleration calculator, and it, along with everything else I talked about, will be in the links in the description. So let's start with our constant acceleration. 8.6 times 10 to the minus 5 meters per second squared. And let's go ahead and assume that our solar ship starts at zero velocity. Let's see how much time it takes us to get to the edge of the solar system. 120 astronomical units is 1.785 times 10 to the 13th meters. So we'll go ahead and plop that in there and calculate. And we get an arrival time of 646,097,407 seconds, just under 20 and a half years. That's a little over half the time that it took the Voyager 1, and that was using gravity assists. This is just using the force of light. Let's do one more bit of math just for fun. The Voyager 1's currently at about 165 astronomical units away, or 2.47 times 10 to the 13th meters. And our solar ship would reach that in just 24 years, whereas the Voyager's been on its mission for almost twice that amount of time. At this point, you might be thinking, wow, this sounds really easy. Why haven't we done this already? Well, it's because the force on the solar ship from light is not the only force acting on it. There's one more big force that we haven't accounted for. This. Because the sun is not just benevolently pushing our solar ship along its way, it's also pulling it back with gravity, We can use Newton's law of universal gravitation to calculate how strong the gravitational force is. The masses of the two objects multiplied by the gravitational constant divided by the distance squared. Or, if you want to be lazy, you can use this gravitational force calculator. I've already put in the information for this situation we were talking about, which is we have object 1 at 2 times 10 to the 30th kilograms, that is our sun, and object 2 at 1,000 kilograms, that's our solar ship. They're one astronomical unit apart because presumably we're launching it from the Earth, and the force on it is 5.96 newtons. Now the problem with that is that our force from our light is only 0.086 newtons. So the force of gravity is about 100 times stronger, pulling it backwards rather than pushing it forwards. Now if we're trying to reduce the force of gravity, the mass of the sun isn't going to change, the universal gravitational constant isn't going to change, and the distance isn't going to change, which means the only thing we can change is the mass of our ship. In order for our 100 meter by 100 meter sail to actually move the ship forward, we need to drop down to somewhere in the range of 10 kilograms instead of 1,000. And now we run into another problem, because 10 kilograms is 10,000 grams, and a 100 by 100 meter sail is 10,000 square meters, which means that each square meter would only have to weigh 1 gram in order for this to work. Actually, I did the math. Every square meter of material could move about 1.46 grams. The next hurdle is what kind of material could possibly be that light? One of the least dense materials I found is a polymer film called Nexevolve Lark CP1, and it has a density of 1.54 grams per cubic centimeter. It looks like this. It's essentially very fancy cling film. Because it's in cubic centimeters and we're looking for square meters, we have to do some math to actually figure out how close this material is to what we need. I could show you all the equations to do that, but at this point, you probably know what I'm going to show you instead. It's a density calculator, because why do more work? Someone's already done it for you. So we have here the density, the volume, and the mass. We're looking for the mass, so all we need is the volume. Put in the density here, 1.54 grams per cubic centimeter. And now for the volume. Let's say we want to do 1 by 1 meter squared just to find out what's going on. We need to decide how thick it's going to be. We need an area of 1 square meter. How thick is that going to be? Let's start with, what if it's 1 meter thick as well? That's going to weigh 1,500 kilograms. Okay, so that's probably not going to work. And if we have it 1 millimeter thick, we get 1.54 kilograms. We're still way, way too heavy. If we go just 10 microns thick, we end up with a weight of about 15 grams, which means that if we go down to 1 micron thick, 1 square meter of this will be able to just about push itself. This is 1.54 grams and 1 square meter pushes 1.46 grams. The problem with that is that CP1 can only get as low as 2.5 microns. Basically, we don't have the materials available which could be light enough to make this make sense on its own. However, the Voyager craft didn't do it on its own. It also used gravitational slingshots. So if we were able to use solar sails in conjunction with other means of propulsion, it could actually work. And when I say it could actually work, I mean it has actually worked, because the LightSail 2 launched in 2019 and landed in 2022. It weighed a little less than 5 kilograms, was the 32 square meter sail, and was able to successfully move using only solar energy. A French company also launched the Gamma Alpha solar sail in 2023. So to summarize, we don't have the materials in order to make solar sails that work completely independently right now, but we do have, in conjunction with other technologies, a way to get started on it, and I for one am super excited. This makes me nerd out. So hopefully you enjoyed the video. That's it for this time. This is a little bit of a preview of the kind of things I've been learning in my mechatronics program, which I started recently. So hopefully you enjoyed that. Special thanks to my super supporters, Zachary W. Collins on Patreon and Lies of J on YouTube, as well as my other supporters, hi Jordan Beagle, Justin Davey, and Mike Zimmerman. You are the ones keeping the videos happening, so thanks very much. If you want to join them on the Wall of Awesome, go ahead and click below. And thanks so much for watching. I'll see you next time.